So here's something you've probably never thought about, and there's no reason you would have. But it's one of those ideas that once it gets into your head, you start seeing it everywhere. Every single fluid you've ever encountered. The water running out of your kitchen tap right now. The air filling your lungs as you breathe. The blood moving through your veins. The coffee you poured this morning. The wind that pushed against you when you stepped outside. Every one of those is doing something that, if you really sit with it, is almost unreasonably complicated. And yet it all looks so simple. Water flows downhill, wind blows, done. What's to explain? Well, a lot actually, quite a lot. Let's start somewhere comfortable. You're lying there and maybe you can hear the faintest hum of air moving through a vent. Or maybe there's a stillness in the room that feels like nothing is happening at all. But even in that stillness, the air around you is a riot of invisible activity. Molecules bumping into each other billions of times a second, pressure waves propagating at the speed of sound, tiny convection currents rising off your body because you're warmer than the room. You are right now submerged in a fluid. You live at the bottom of an ocean of air, and you've been swimming in it your whole life without ever really thinking of it that way. And that's kind of the central magic trick of fluid dynamics. The subject is everywhere. It governs weather, flight, blood flow, ocean currents, the way smoke curls off a candle, the way cream swirls into coffee. And yet, for most of human history, nobody had any real framework for understanding it. People could observe fluids. They could use them, channel them, float on them, drown in them. But actually describing what a fluid does, mathematically, in a way that lets you predict its behavior, that turned out to be one of the hardest problems in all of science. And in some very real ways, it still is. But let's not get ahead of ourselves. Let's go back. Way back. The ancient Greeks, as they tended to do with most things, got there first. Or at least, they were among the first to leave written records of thinking carefully about how fluids behave. And the person you want to know about is Archimedes. You've heard the name. You probably know the bathtub story, the one where he jumps out of the bath shouting "Eureka" and runs naked through the streets of Syracuse. That story might be apocryphal, honestly. It was written down by Vitruvius a couple of centuries after Archimedes lived, so take it with a grain of salt. But the principle behind the story? That's absolutely real, and it's beautiful in its simplicity. Here's what Archimedes figured out, sometime around 250 BC. When you put an object in water, the water pushes back on it. Not randomly, not vaguely. It pushes back with a force exactly equal to the weight of the water that the object displaced. So if you lower a block of wood into a basin and the water level rises, the volume of water that got pushed up and out of the way, the weight of that displaced water, is exactly the upward force acting on the block. That's why the block floats. The upward push from the water matches or exceeds the weight of the wood, pulling it down. Think about what that means for a second. It means buoyancy isn't some mysterious property of certain materials. It's a relationship. It's about density, how much mass is packed into a given volume. If the object is less dense than the fluid it's sitting in, it floats. If it's denser, it sinks. A steel ball sinks in water because steel is much denser than water. But a steel ship floats because the ship isn't solid steel. It's a thin shell enclosing a huge volume of air. And the average density of the whole ship, air and all, is less than the density of water. That's it. That's the whole trick. And Archimedes didn't just state this as a vague idea. He proved it geometrically, rigorously, in a treatise called On Floating Bodies. This was around 250 BC, remember. No calculus, no algebra as we know it, No concept of force in the Newtonian sense, just geometry and brilliant reasoning. He worked out the stability conditions for floating objects, under what circumstances a floating body would right itself if tilted, and when it would tip over. If you've ever been in a canoe and felt that nervous wobble, that's exactly the problem Archimedes was analyzing 2,000 years before you were born. Now, here's the thing about Archimedes. He was working in Syracuse, on the island of Sicily, during a period when Rome was expanding aggressively across the Mediterranean. Syracuse was a Greek city-state, and it found itself besieged by Roman forces during the Second Punic War, around 214 to 212 BC. Archimedes, by this point, an old man, reportedly designed war machines to defend the city. Cranes that could lift Roman ships out of the water, catapults, possibly some kind of mirror array to focus sunlight and set ships on fire, though that last one is heavily debated. The point is, here was a man who understood fluids and mechanics deeply enough to weaponize that knowledge. When Syracuse finally fell, a Roman soldier killed Archimedes, reportedly while he was working on a mathematical problem in the sand. The Roman general Marcellus was supposedly furious. He'd given orders to capture Archimedes alive, but it was too late. And with Archimedes gone, something strange happened, or rather, something didn't happen. For nearly 1,800 years, nobody really advanced the science of fluid behavior much beyond where he'd left it. That's not entirely fair. There were practical advances in hydraulic engineering, especially in Rome. The Romans were extraordinary builders of aqueducts and water distribution systems. They moved water across valleys and through mountains to supply their cities using gravity and carefully calculated gradients. The Pont du Gard in southern France, built around 19 BC, carried water across the Garden River Valley and dropped only about 17 meters over its entire 50-kilometer length. That's a gradient of roughly 1 in 3,000, incredibly precise for a civilization working without modern surveying tools. But the Romans were engineers in the most practical sense. They knew what worked. They could build things that moved water reliably. What they didn't do, what they didn't seem particularly interested in doing, was develop a theoretical framework for why fluids behave the way they do. They didn't write down equations. They didn't formalize the relationship between pressure and flow. They built brilliantly, but they built from experience and accumulated craft knowledge, not from physics. And so for a very long time, the understanding of fluids remained largely empirical. People knew that water flows downhill. They knew that wind could push a sailing ship. They knew that some liquids were thicker than others. Honey pours more slowly than wine. But the deeper questions: why does water speed up when a river narrows? Why does smoke rise and then break into turbulent swirls? Why does a spinning ball curve in flight? Those questions sat there, unanswered, waiting. The person who really starts to crack things open is someone you might not immediately associate with fluid dynamics, but you should: Leonardo da Vinci. Yes, that Leonardo, the painter, the inventor, the anatomist, the restless genius of the Italian Renaissance. Leonardo was obsessed with water, absolutely obsessed. If you look through his notebooks, and thousands of pages survive, you'll find sketch after sketch of water in motion. Vortices, waves, currents flowing around obstacles, water pouring from sluice gates, rivers eroding their banks. He drew water the way he drew human muscles, with intense, almost compulsive attention to the patterns of movement. And Leonardo noticed things. He noticed that when water flows through a narrow channel, it speeds up. He noticed that the speed of water at the surface of a river is different from the speed at the bottom. He noticed that when water flows past a cylindrical obstacle, like a bridge pier, It creates swirling vortices downstream. Those beautiful rhythmic patterns that we now call the von Karman vortex street, though that name wouldn't come along for another 400 years. Leonardo was seeing turbulence, really seeing it, and trying to capture it on paper. He even articulated something close to what we now call the continuity principle. The idea that in a steady flow, the amount of fluid passing through one cross-section of a channel has to equal the amount passing through any other cross-section. If the channel narrows, the fluid has to speed up to keep the same volume flowing through. Think of it like a crowd of people walking down a wide hallway that suddenly narrows to a single doorway. Everyone has to squeeze through, so they move faster at the bottleneck. Same number of people per minute passing through, but compressed into a smaller space, so they're moving quicker. Leonardo grasped this intuitively, maybe even quantitatively, from watching rivers and canals in the Italian countryside. But here's the frustrating part about Leonardo. He never published any of it. His notebooks were private, written in his famous mirror script, and after his death in 1519, they were scattered, lost, rediscovered, scattered again. His observations about fluid flow didn't enter the scientific conversation in any meaningful way. The insights were real, they were brilliant, but they were locked away. So the formal science of fluid dynamics had to be reinvented, essentially from scratch, by people who never read a word Leonardo wrote about water. And that reinvention starts in earnest in the 17th century with the scientific revolution, when people like Galileo and Newton began building the mathematical tools that would make a real theory of fluids possible. But before we get to Newton, and we will, because Newton's contribution to this story is both profound and, in a way, hilariously wrong about one specific thing. Let's talk about pressure for a moment. Pressure is one of those words you use all the time without really thinking about what it means physically. You check the air pressure in your tires. The weather report mentions high pressure systems. Your doctor measures your blood pressure. But what is it really? Here's a way to think about it. Imagine you're holding a brick. That brick weighs, let's say, a couple of kilograms. Now set it flat on your open palm. You feel the weight spread across your whole hand. Manageable. Now flip the brick so it's standing on its narrow edge, balanced on your palm. Same brick, same weight. But now all that force is concentrated on a much smaller area. It digs in. It hurts. That's pressure. It's force divided by the area over which that force is applied. Same force, smaller area, higher pressure. In a fluid, pressure works the same way, but it acts in every direction simultaneously. That's one of the things that makes fluids different from solids. If you push on a solid block, the force transmits in the direction you pushed. But if you squeeze a balloon, the air inside pushes back equally in all directions, against the top, the bottom, the sides, everywhere. Fluid pressure is omnidirectional, and it increases with depth, because the deeper you go, the more fluid is stacked above you, pressing down with its weight. The person who formalized this idea was Blaise Pascal, the French mathematician and philosopher, working in the 1640s and 1650s. Pascal showed that pressure applied to an enclosed fluid is transmitted undiminished throughout the entire fluid. Push on one spot, and the pressure increase shows up everywhere, equally. This is Pascal's principle, and it's the reason hydraulic systems work. Think about the brakes in your car. You press the brake pedal with your foot, and that force gets transmitted through brake fluid, an incompressible liquid in a sealed system, to the brake pads at all four wheels. Your foot pushes a small piston. The fluid transmits that pressure to larger pistons at the wheels, and because pressure equals force divided by area, A larger piston area means a larger output force. You're amplifying your leg strength through fluid pressure. That's Pascal, working for you every time you slow down at a red light. And right around the same time Pascal was thinking about pressure, something wonderful was happening in Italy. Evangelista Torricelli, a student of Galileo, was trying to answer a practical question that had been bugging engineers for years. Pump operators in the mines of Tuscany had noticed that their suction pumps could only lift water about 10 meters. No matter how good the pump was, the water just wouldn't rise any higher. Why? Torricelli's insight in 1643 was elegant. He realized that it wasn't the pump pulling the water up, it was the atmosphere pushing it up. The pump creates a partial vacuum above the water column, and atmospheric pressure pushing down on the water surface outside the pump drives the water up into the low-pressure region. But atmospheric pressure is finite. It can only support a column of water about 10 meters tall, because that's the height at which the weight of the water column exactly balances the pressure of the atmosphere. Go any higher, and there's simply not enough atmospheric push to hold the water up. To prove this, Torricelli did something clever. Instead of water, he used mercury, which is about 13.5 times denser than water. If atmospheric pressure can support 10 meters of water, it should only support about 760 millimeters of mercury, a much more manageable height to work with in a laboratory. He filled a glass tube with mercury, inverted it into a dish of mercury, and watched the mercury level drop to exactly that predicted height, leaving a vacuum above it. He just invented the barometer, and more than that, he demonstrated that we live under a blanket of air that has real, measurable weight, pressing down on everything with a force of roughly 10,000 kilograms per square meter at sea level. Think about that. Right now, as you lie there, the atmosphere is pressing down on every square centimeter of your body with a force of about 1 kilogram. You don't feel it because the pressure inside your body pushes outward with the same force, so it all balances out. But it's there. You are, quite literally, at the bottom of a pressurized ocean of air, and Torricelli was the first person to measure exactly how heavy that ocean is. Now, Torricelli died young. He was only 39, and he didn't get to push his ideas much further. But the tools were being assembled. Pressure, buoyancy, the behavior of fluids at rest. These pieces were falling into place. What was still missing was a way to describe fluids in motion. Static fluids, fluids just sitting there, were hard enough. But flowing fluids? Fluids swirling, accelerating, splitting around obstacles, mixing and churning. That was a different beast entirely, and the person who would take the first real crack at the mathematics of moving fluids was someone whose name you already know, though probably not for this particular contribution. Isaac Newton had a few things to say about how fluids resist being pushed around, and what he came up with was both groundbreaking and, in one very specific way, not quite right. A mistake that would take more than a century to sort out, and that would lead to one of the most famous paradoxes in all of physics. It's called D'Alembert's paradox, and we'll get to it. But first, let's talk about what Newton actually did. So Newton, in his monumental work, The Principia, published in 1687, a book that essentially rewrote the rules of the universe, buried in among the laws of motion and the theory of gravitation, there's a section where he turns his attention to how objects move through fluids. And his approach was, in a way, very Newtonian, very mechanical. He imagined a fluid as being made up of tiny individual particles, like a stream of little pellets. And he asked, if an object is moving through this stream of pellets, How much resistance does it feel? How hard do the pellets push back? His answer was elegant and intuitive. He said the resistance depends on how fast the object is moving, how big it is, and how dense the fluid is. Move faster, and you hit more pellets per second, and each pellet hits harder. Make the object bigger, and it sweeps through more of them. Put it in a denser fluid, and each pellet carries more mass. All of that makes perfect sense, and it's broadly correct. But here's where Newton introduced something really important. His concept of what we now call viscosity, though he didn't use that exact word. He described how layers of fluid slide past each other, and he proposed that the resistance between those layers is proportional to how fast they're sliding. Double the speed difference between two layers, and you double the friction between them. This is what we call a Newtonian fluid, and it's actually a pretty good description of how a lot of common fluids behave. Water, air, most oils, they follow Newton's rule reasonably well. The relationship between the sliding speed and the internal friction is linear. Nice and clean. But here's the thing. Not all fluids play by those rules. Ketchup, for instance. You know how ketchup just sits there in the bottle, stubbornly refusing to move, and then suddenly it all comes out at once. That's because ketchup is what's called a shear thinning fluid. The harder you push it, the more shear stress you apply, the less viscous it becomes. It's the opposite of what Newton described. Blood is similar, actually. It flows more easily when it's moving fast through your arteries. Cornstarch mixed with water does the opposite. It gets thicker when you push it harder, which is why you can run across a pool of it, but you'll sink if you stand still. These are all non-Newtonian fluids, and they're everywhere in daily life. But Newton's framework couldn't account for them. That wasn't really his fault. He was building the first mathematical model, and it captured the most common behavior beautifully. But it's worth knowing that the very first model of fluid friction was, from the start, an approximation that only works for certain fluids. Now, the bigger problem with Newton's approach wasn't about viscosity. It was about how he modeled the fluid itself. Remember, he treated it as a collection of independent particles, like a hail of tiny balls bouncing off the surface of a moving object. And in this model, the particles don't interact with each other. They don't push their neighbors out of the way. They don't form waves or eddies or currents. They just bounce. And this leads to some predictions that are, well, wrong. Specifically, Newton's particle model predicts that the drag on an object, the resistance it feels as it moves through a fluid, depends on the shape of the front of the object, but not the back. In his model, the back side is essentially in a shadow, sheltered from the hail of particles, so its shape doesn't matter. And that's just not what happens in real life. The shape of the back of a car matters enormously for its aerodynamic drag. The tapering tail of an airplane fuselage isn't decorative. What happens behind an object, the wake, the turbulence, the low pressure region that forms and sucks backward, that's a huge part of the story. But Newton's model missed it entirely. And this is where things get really interesting, because the next person to pick up the thread was Daniel Bernoulli, and he approached the problem from a completely different direction. Bernoulli came from one of the most remarkable families in the history of mathematics. The Bernoullis were a Swiss family originally from Basel, and over the course of about 3 generations, they produced something like 8 significant mathematicians and scientists. It's almost absurd. Daniel's father, Johann, was a brilliant mathematician. His uncle, Jakob, was also a brilliant mathematician. And they were all, by most accounts, intensely competitive with each other to the point of genuine nastiness. Johann Bernoulli, Daniel's father, was so jealous of his own son's achievements that when Daniel won a prestigious prize from the French Academy of Sciences, and Johann had also entered the same competition, Johann was furious. Some accounts suggest he tried to claim credit for Daniel's work. He may have even kicked Daniel out of the house. The Bernoulli family gatherings must have been something else. But Daniel Bernoulli, despite all that family drama, produced something extraordinary. In 1738, he published a book called Hydrodynamica. And yes, that's where the word hydrodynamics comes from. And in this book, he laid out a principle that you've probably heard of, even if you don't remember exactly what it says. Bernoulli's principle. Here's what it comes down to, and it's one of those ideas that sounds simple, but has enormous consequences. When a fluid speeds up, its pressure drops. When it slows down, its pressure rises. That's it. Speed and pressure are linked in a flowing fluid, and they move in opposite directions. Now, why would that be true? Think about it this way. Imagine water flowing through a pipe, and the pipe narrows at one point. The same amount of water has to get through the narrow section as through the wide section. There's nowhere else for it to go. So the water has to speed up in the narrow part. It's like cars merging from 4 lanes into 2. Everything has to move faster to maintain the same flow rate. That's actually the continuity principle that Leonardo da Vinci sketched in his notebooks 2 centuries earlier, finally getting its mathematical treatment. But here's what Bernoulli added, that speeding up doesn't come for free. The energy to accelerate the fluid has to come from somewhere, and it comes from the pressure. The fluid trades pressure for speed. In the narrow section, the water moves faster, but pushes less hard on the walls of the pipe. In the wide section, it moves slower, but pushes harder. And this is where you can start to see why airplanes fly. I know. The full story of how wings generate lift is more complicated than the version you might have heard in school, and there are some genuinely misleading explanations floating around out there. But Bernoulli's principle is a real part of it. Air flowing over the curved top of a wing has to travel faster than the air flowing under the flatter bottom. Faster air means lower pressure on top. Higher pressure on the bottom pushes up. That pressure difference is lift. It's not the whole story. The angle of the wing matters enormously, and the way the wing deflects air downward is arguably even more important. But Bernoulli's insight is genuinely in there, doing real work. You can feel this principle yourself, by the way. If you've ever held a piece of paper by its edge and blown across the top of it, you've seen the paper rise. The fast-moving air from your breath lowers the pressure above the paper, and the still air underneath pushes it up. That's Bernoulli, right there in your hands. But here's what's really clever about how Bernoulli arrived at this. He didn't just observe it. He derived it from first principles, using the idea of conservation of energy. He was one of the first people to apply energy concepts to fluid flow. A fluid has kinetic energy when it's moving, and it has potential energy from its pressure and its height. Bernoulli said these forms of energy have to balance. If the fluid gains kinetic energy by speeding up, it has to lose an equal amount of pressure energy. It's like a ball rolling down a hill. It trades height for speed. A fluid flowing through a narrowing pipe trades pressure for speed. Same idea, different form. Now, Bernoulli's work was groundbreaking, but it came with a significant limitation, and this is important. His equations assumed the fluid had no viscosity, no internal friction at all. He was describing what's called an ideal fluid, or sometimes an inviscid fluid. a fluid that flows without any resistance between its layers, without any stickiness, without any energy being lost to heat. And this is a beautiful mathematical simplification, but it creates a problem. Because real fluids do have viscosity. Water is fairly thin, but it's not zero. Honey is thick. Air is thin, but it's still not nothing. And when you ignore viscosity entirely, you get predictions that work wonderfully in some situations and fail spectacularly in others. This is exactly the trap that the great French mathematician Jean-Laurent d'Alembert fell into. D'Alembert was a fascinating figure. He was a foundling, abandoned as a baby on the steps of the Saint-Jean-Laurent church in Paris in 1717, which is where his name comes from. He was raised by a glazier's wife, and he grew up to become one of the leading mathematicians and philosophers of the Enlightenment. He co-edited the famous Encyclopédie with Diderot, and in 1752 he published a result about fluid flow that was mathematically impeccable and physically impossible. He proved, rigorously, correctly, using the best mathematical tools available, that a body moving through an ideal, inviscid fluid should experience zero drag. None. No resistance at all. A ball moving through a perfect fluid would just keep going forever, feeling no pushback whatsoever. Now this is obviously absurd. You know from walking through wind, from swimming in a pool, from stirring a cup of tea, that fluids resist motion. Drag is real. You feel it every time you stick your hand out of a car window. But D'Alembert's mathematics said it shouldn't exist, and his mathematics was correct. The problem wasn't in his logic, it was in his assumptions. He'd assumed an ideal fluid with no viscosity, and in such a fluid, the math really does predict zero drag. The fluid parts smoothly in front of the object, flows around it in perfect symmetry, and closes up behind it just as neatly. The pressure pushing on the front is exactly balanced by the pressure pushing on the back. Everything cancels out. No net force. This became known as D'Alembert's paradox, and it haunted fluid dynamics for generations. It was embarrassing, honestly. Here was this beautiful, rigorous mathematical framework that gave a physically absurd answer. It meant that the theory of ideal fluids, for all its elegance, was missing something fundamental. And what it was missing, of course, was viscosity, that internal friction that Newton had first tried to describe. The real fluid doesn't close up neatly behind a moving object. It separates. It forms a wake. Eddies spin off. A low-pressure region develops behind the object, and that pressure imbalance is what creates drag. But capturing all of that mathematically required tools that didn't exist yet in D'Alembert's time. The people who would finally build those tools were working in the early 19th century, and the equations they produced are so important, so central to everything that came after, that they're still the governing equations of fluid dynamics today, nearly 200 years later. They're called the Navier-Stokes equations, and they are, without exaggeration, some of the most important and most difficult equations in all of physics. The story of how they came together involves a French engineer, a British mathematician, and a problem so hard that there's literally $1 million prize waiting for anyone who can prove it's well-behaved. Let's talk about that prize, and let's talk about those two people, because the story is fascinating. The French engineer was Claude-Louis Navier. Born in 1785, he lost his father at a young age and was raised in part by his uncle, Émilien Gautier, who happened to be one of France's most respected civil engineers. So Navier grew up surrounded by practical engineering problems, bridges, canals, roads. He attended the École Polytechnique in Paris, which at that time was arguably the finest technical school in the world, and then the École des Ponts et Chaussées, the School of Bridges and Roads. which is exactly as practical as it sounds. Navier was not a pure mathematician sitting in a tower. He was a man who designed bridges, who supervised construction projects, who cared about how water actually moved through channels and pipes because his job depended on getting that right. And in 1822, Navier presented a paper to the French Academy of Sciences in which he derived a set of equations describing the motion of a viscous fluid. Now, here's what's interesting about how he got there. Navier was thinking about fluids at the molecular level. He imagined the molecules of a fluid exerting forces on each other, attractive and repulsive forces that depended on the distances between them. He built his equations from that molecular picture, and what he arrived at was a set of partial differential equations that included terms for pressure, for the velocity of the fluid, for the forces acting on it like gravity, and crucially, for the internal friction, the viscosity, that D'Alembert's ideal fluid theory had left out. The thing is, Navier's molecular reasoning had some shaky steps. His derivation worked, but the physical justification for some of his assumptions wasn't entirely rigorous. He got the right answer, arguably, for reasons that weren't perfectly sound. And that's where the British mathematician comes in. George Gabriel Stokes was born in Ireland in 1819, so he was a generation younger than Navier. He studied at Cambridge, where he turned out to be spectacularly good at mathematics. He was the senior wrangler in 1841, meaning he scored highest on the fearsome mathematical Tripos exam. Stokes was a different kind of thinker than Navier. Where Navier came at the problem from an engineering and molecular perspective, Stokes approached it as a continuum mechanics problem. He didn't worry about individual molecules. Instead, he treated the fluid as a continuous substance and asked, what are the stresses inside this fluid, and how do they relate to the way the fluid is deforming? In 1845, Stokes published his own derivation of essentially the same equations Navier had arrived at, but from this completely different starting point. Stokes's derivation was more general and more mathematically rigorous. He carefully laid out the assumptions that the fluid is a continuum, that the stress depends linearly on the rate of strain, that the fluid is isotropic, meaning its properties are the same in every direction. And from those assumptions, he derived the equations cleanly. So you had two people working in different countries from different intellectual traditions arriving at the same set of equations. That's always a good sign in science. When different paths lead to the same destination, it usually means you've found something real. And so these equations carry both their names, the Navier-Stokes equations. Let me try to give you a feel for what these equations actually say without writing them on a board, because obviously you're just listening. Think of it this way. Imagine you're tracking a tiny little parcel of fluid, a little blob of water, say, drifting along in a river. The Navier-Stokes equations are basically Newton's second law, force equals mass times acceleration, applied to that little blob. They say that the acceleration of that fluid parcel equals the sum of all the forces acting on it, divided by its mass. Simple enough in concept, right? But here's where it gets complicated. The forces acting on that little blob include pressure forces. The fluid around it is pushing on it from all sides, and if the pressure is higher on one side than the other, the blob gets pushed. There are gravity forces pulling it down. And then there are the viscous forces, the friction from the fluid around it, the neighboring fluid dragging on it or being dragged by it. That viscous term is what Navier and Stokes added to the picture, and it's what makes these equations different from the earlier ideal fluid equations that Euler had written down. Now, the acceleration term is tricky too, because the fluid is moving. The blob is being carried along by the flow, and the flow itself is changing from place to place and moment to moment. So the acceleration of the blob depends not just on how the velocity at its location is changing in time, but also on the fact that the blob is moving to a new location where the velocity might be different. This is called the convective acceleration, and mathematically, it makes the equations nonlinear. That word, nonlinear, is the source of almost all the difficulty. Let me explain what nonlinear means in a way that's intuitive. A linear equation is one where the output is proportional to the input. Double the input, double the output. Everything scales neatly. You can add solutions together and get another solution. Linear equations are, relatively speaking, friendly. Nonlinear equations are the ones where the output doesn't scale proportionally with the input, where doubling one thing might quadruple another, or where two effects interact and produce something entirely unexpected. Nonlinear equations can produce chaos, literally in the mathematical sense. Tiny differences in starting conditions can lead to wildly different outcomes, and the Navier-Stokes equations are deeply, fundamentally nonlinear because the velocity of the fluid appears in both the thing being solved for and the thing doing the transporting. The fluid carries itself. Its own motion determines where it goes next, which changes its motion, which changes where it goes. It's like trying to predict the path of a leaf in a stream, except the leaf is also somehow shaping the stream as it moves. This is why, nearly 200 years after Navier first wrote these equations down, we still can't solve them in general. And I mean that in a very specific, technical sense. For certain simplified situations, very slow flow, very symmetric geometries, very special boundary conditions, people have found exact solutions. Stokes himself solved the case of extremely slow, creeping flow around a sphere, which is why that regime is called Stokes flow. There are solutions for flow in a pipe, flow between parallel plates, a few other idealized cases. But for the general case, turbulent flow around a complicated shape, the kind of flow you actually encounter in the real world, nobody has ever found a general analytical solution. Nobody has even proven that smooth, well-behaved solutions always exist. And that brings us to the $1 million prize. In the year 2000, the Clay Mathematics Institute in Cambridge, Massachusetts, identified 7 problems they considered the most important, unsolved problems in mathematics. They called them the Millennium Prize problems, and they offered $1 million for the solution to each one. The Navier-Stokes existence and smoothness problem is one of them. The question, roughly stated, is this: if you start with smooth, reasonable initial conditions, a fluid that's moving in some well-defined way at time 0, can you prove that the Navier-Stokes equations will always produce a smooth, well-defined solution for all future time? Or is it possible that the equations could develop singularities, points where the velocity or pressure blows up to infinity in finite time? Think about what that question is really asking. It's asking whether the fundamental equations governing fluid motion are mathematically consistent, whether they can, in some situations, predict physically impossible things like infinite velocity. And as of right now, nobody knows the answer. More than 20 years after the prize was announced, it remains unclaimed. Some of the most brilliant mathematicians in the world have spent careers working on it. There have been partial results, progress on simplified versions of the problem, insights that illuminate pieces of the puzzle. But the full answer remains elusive. And here's what's kind of remarkable about that. We use these equations every single day. Every weather forecast you've ever seen is based on numerical solutions to the Navier-Stokes equations. Every airplane that's been designed in the last several decades has been tested using computational fluid dynamics software that solves discretized versions of these equations on massive computer grids. Engineers designing everything from car bodies to artificial heart valves to ventilation systems in buildings are running Navier-Stokes simulations. The equations work. They give answers that match reality extraordinarily well. We just can't prove, in the pure mathematical sense, that they always will. It's a strange situation if you think about it. We have equations that are almost certainly correct. They've been validated against experiments countless times. But we can't fully understand their mathematical behavior. We're in the position of using a tool that works brilliantly in practice, while not being entirely sure, in theory, that it won't someday surprise us. Now, there's another piece of this story that I think is really worth slowing down for, because it connects everything we've been talking about. The ideal fluid theory, the viscous corrections, D'Alembert's paradox, and it involves one of the most important conceptual breakthroughs in all of fluid dynamics. It came from a German engineer named Ludwig Prandtl, and it happened at a mathematics conference in Heidelberg in 1904. Prandtl was 30 years old, a professor at the Technische Hochschule in Hanover, and he gave a short talk, just 8 pages in the published proceedings, that completely transformed how people thought about fluid flow. His idea was deceptively simple, and it resolved D'Alembert's paradox in the most elegant way imaginable. Here's what Prandtl realized. When a real fluid flows past a solid surface, say air flowing over an airplane wing, or water flowing past the hull of a ship, the fluid right at the surface doesn't move. It sticks. This is called the no-slip condition, and it's a consequence of viscosity. The molecules of fluid right at the wall are essentially held in place by their interaction with the wall, but the fluid far away from the surface is moving at the full speed of the flow. So somewhere between the wall and the free stream, the velocity has to transition from 0 to full speed. Prandtl's insight was that this transition happens in a very thin layer right next to the surface, a layer he called the boundary layer. And here's the key. Within that thin boundary layer, viscosity matters enormously. The velocity is changing rapidly over a very short distance, which means the viscous shearing forces are large. But outside the boundary layer, in the bulk of the flow, the fluid behaves almost exactly like the ideal, inviscid fluid that Euler and Bernoulli and D'Alembert had analyzed. The viscous effects are negligible out there. So Prandtl was saying, both theories are right, but they apply in different regions. The ideal fluid theory works beautifully for the outer flow. The viscous theory is essential inside the boundary layer, and the two regions are coupled. What happens in the boundary layer affects the outer flow, and vice versa. D'Alembert's paradox isn't really a paradox at all. The ideal fluid theory predicts zero drag because it's ignoring the boundary layer, which is exactly where the drag is generated. The viscous friction in that thin layer creates shear stress on the surface. That's skin friction drag. And when the boundary layer separates from the surface, which happens when the flow can't maintain enough momentum to follow the surface's curvature, you get that wake, that low-pressure region behind the object, and that's pressure drag, or form drag, 8 pages. That's all it took. And yet, the implications were enormous, because suddenly, engineers had a framework for thinking about fluid flow that was both mathematically tractable and physically realistic. You didn't have to solve the full Navier-Stokes equations everywhere. You could solve the simpler inviscid equations for the outer flow, solve the boundary layer equations, which Prandtl also derived, and which are much simpler than the full Navier-Stokes equations, near the surface, and patch the two solutions together. This was transformative for aerodynamics in particular, because the early 20th century was exactly when powered flight was becoming real. The Wright brothers had flown at Kitty Hawk just the year before Prandtl's paper, in December 1903, and the aviation engineers of that era desperately needed tools for predicting how air would behave around wings. Prandtl gave them those tools. His boundary layer concept, combined with his later work on wing theory and induced drag, essentially created the field of modern aerodynamics. His students and collaborators, Theodor von Karman, Max Munkh, Jakob Ackeret, and others, went on to shape aviation and rocket science for decades. But there's another layer to the boundary layer story, if you'll forgive the pun, and it connects to something we haven't really talked about yet, something that remains, even today, the single hardest problem in classical physics. It's the reason weather forecasts go wrong after about 10 days. It's the reason your coffee does that swirling thing when you pour in the cream. It's the reason a river sounds the way it does. And it has a name that you've probably heard before, even if you've never studied physics. It's called turbulence. And the boundary layer is exactly where the story of turbulence often begins. Because here's what happens inside that thin layer of fluid clinging to a surface. At the very front edge of, say, an airplane wing, where the air first makes contact, the boundary layer starts out smooth. The fluid moves in neat, orderly sheets, each layer sliding over the one beneath it like pages in a book. This is called laminar flow, from the Latin word lamina, meaning a thin plate or layer, and it's beautiful, in a way, predictable, mathematically elegant. If you could somehow visualize it, you'd see these perfectly parallel streamlines, all flowing in the same direction, all well-behaved, but it doesn't last. As the flow moves further along the surface, something starts to happen. Tiny disturbances, maybe a microscopic bump on the surface, maybe a faint vibration, maybe just the inherent instability of the flow itself, begin to grow. They amplify. The smooth layers start to wobble, then ripple, and then, quite suddenly, the whole thing breaks down into a churning, chaotic mess. The streamlines tangle, eddies form, swirl, break apart, form again. Velocity at any given point starts fluctuating wildly, moment to moment. The flow has become turbulent, and this transition, this shift from laminar to turbulent flow, is one of the most important phenomena in all of fluid dynamics. It changes everything: how much drag a surface experiences, how efficiently heat transfers, how much energy you need to pump fluid through a pipe, how loud a jet engine is. Understanding when and why it happens has been an obsession of physicists and engineers for over a century and a half. And we still don't fully understand it. The person who first brought real scientific rigor to the question was Osborne Reynolds, an Irish-born engineer working at Owens College in Manchester, what's now the University of Manchester. In 1883, Reynolds published a paper describing a beautifully simple experiment. He set up a long glass tube with water flowing through it, and he injected a thin stream of dye into the center of the flow. At low flow speeds, the dye stream stayed perfectly coherent, a clean, straight line running down the middle of the tube, laminar flow. But as he gradually increased the speed, there came a point where the dye stream began to waver, and then, quite abruptly, it broke apart and mixed completely into the surrounding water. The flow had gone turbulent. What Reynolds figured out, and this was the real insight, was that the transition didn't depend on velocity alone. It depended on a combination of factors: the velocity of the flow, the diameter of the pipe, and the viscosity of the fluid. He combined these into a single dimensionless number: velocity times diameter divided by kinematic viscosity, and showed that the transition from laminar to turbulent flow happened at roughly the same value of this number, regardless of which specific fluid you were using or how big the pipe was. That number is now called the Reynolds number, and it is arguably the single most important dimensionless quantity in all of fluid mechanics. Think about what that means. It means that a tiny pipe carrying fast-moving water can have the same Reynolds number as a massive duct carrying slow-moving air, and the character of the flow, whether it's laminar or turbulent, will be the same. This is a scaling law, and it's incredibly powerful. It's the reason engineers can test scale models of airplanes in wind tunnels and get meaningful results. As long as you match the Reynolds number, the flow patterns will be similar. This principle, called dynamic similarity, is one of the foundational tools of experimental fluid dynamics, and it all traces back to Reynolds and that glass tube in Manchester. Now, for pipe flow, the critical Reynolds number, the value where turbulence kicks in, is roughly around 2300. Below that, flow tends to stay laminar. Above it, turbulence becomes increasingly likely. But here's the thing. That number isn't as clean and sharp as it sounds. Reynolds himself noticed that with very careful experimental conditions, he could maintain laminar flow at Reynolds numbers well above 2300, sometimes up to 10,000 or even higher. The flow was metastable, laminar but fragile, like a ball balanced on top of a hill. The slightest disturbance would trigger the transition. And this sensitivity to disturbances is one of the things that makes turbulence so maddeningly difficult to predict from first principles. So what actually is turbulence, physically? This is where it gets genuinely hard, because turbulence isn't a single phenomenon you can point to. It's a state of flow characterized by several features all happening at once. There's irregularity. The velocity at any point fluctuates seemingly randomly in time. There's diffusivity. Turbulent flow mixes things much more effectively than laminar flow, which is why your cream mixes into your coffee so quickly once those swirling motions start. There's vorticity. Turbulence is full of spinning structures, eddies of all different sizes, rotating and stretching and interacting with each other. And there's dissipation. Turbulence constantly converts kinetic energy into heat through viscous friction, which means it needs a continuous supply of energy to sustain itself. Cut off the energy source, and turbulence dies. One of the most beautiful descriptions of turbulent structure came from Lewis Fry Richardson, a British mathematician and physicist who, in 1922, wrote a little rhyme that captures something profound. He wrote, "Big whirls have little whirls that feed on their velocity, and little whirls have lesser whirls, and so on to viscosity." What Richardson was describing is what we now call the energy cascade. In a turbulent flow, energy enters at the largest scales, the big eddies, the ones set by the overall geometry of the flow, like the width of a river or the chord of a wing. These large eddies are unstable, and they break down into smaller eddies, which break down into still smaller ones, and so on, cascading energy down through a whole spectrum of sizes until you reach eddies so tiny that viscosity can finally do its work and convert their kinetic energy into heat. This smallest scale is called the Kolmogorov microscale, named after Andrei Kolmogorov, the Soviet mathematician who, in 1941, developed the statistical theory that describes this cascade. And Kolmogorov's work is worth pausing on for a moment because it represents one of the few genuine theoretical triumphs in the study of turbulence. Kolmogorov didn't try to solve the Navier-Stokes equations for turbulent flow. Nobody can do that. Instead, he made a series of assumptions about the statistical properties of turbulence at very small scales. He assumed that at scales much smaller than the big energy-containing eddies, the turbulence would be statistically isotropic, meaning it looks the same in every direction, and that its character would depend only on two things: the rate at which energy is being dissipated and the viscosity of the fluid. From these assumptions, using dimensional analysis, which is essentially the art of figuring out what form an equation must take based on the units of the quantities involved, he derived predictions about how the energy in turbulent flow is distributed across different eddy sizes. His famous result, the Kolmogorov 5/3 law, says that the energy at a given scale falls off as the 5/3 power of the wave number. And this prediction has been confirmed experimentally in an extraordinary range of turbulent flows, from laboratory jets to atmospheric turbulence to ocean currents. It's one of those rare cases where a relatively simple theoretical argument gives you a result that holds up across wildly different physical situations. But here's the kicker. Kolmogorov's theory tells you about the statistics of turbulence. It tells you about averages, about energy spectra, about the probability distributions of velocity fluctuations. What it doesn't tell you is what the flow will do at any specific instant. And that's the fundamental challenge. Turbulence is deterministic. It's governed by the Navier-Stokes equations, which are completely deterministic. There's no randomness in the equations themselves, and yet the solutions are so exquisitely sensitive to initial conditions that for all practical purposes, you can't predict the detailed behavior of a turbulent flow beyond a certain time horizon. This is chaos, in the mathematical sense. And it's why Richardson, who we just mentioned, was also a pioneer in weather prediction. He understood, earlier than most, that the atmosphere is a turbulent fluid, and that predicting its behavior would require tracking motions across an enormous range of scales. Richardson actually attempted, by hand, to compute a numerical weather forecast during World War I. He divided a region of Europe into a grid, wrote down the governing equations at each grid point, and spent months doing the arithmetic. His forecast was wildly wrong. It predicted a pressure change of 145 millibars in 6 hours, which would basically be an apocalyptic storm. The real pressure change was nearly zero. But the failure wasn't in his method. It was in his initial data, which was too coarse and too inaccurate, and in the fact that he couldn't resolve the small-scale motions that affect the large-scale ones. He was ahead of his time by decades. He imagined, in a remarkable passage in his 1922 book, a vast forecast factory, a giant hall filled with thousands of human computers, each one calculating the weather for one small region of the globe, all coordinated by a conductor standing on a central pillar. It's a haunting image, because what he described is essentially what modern supercomputers do today when they run weather models. He just didn't have the machine to do it. And this connection between turbulence and computation is deep and important, because the practical reality of turbulence in engineering is that you almost always have to compute your way through it. You can't solve the equations analytically. You can use Kolmogorov's theory to understand the statistical structure, and that's valuable. You can use Reynolds' number to predict when turbulence will occur, and that's essential. But when you need to know the actual forces on an actual airplane wing, or the actual mixing in an actual combustion chamber, or the actual heat transfer in an actual nuclear reactor cooling system, you need to solve the equations numerically. And this is where the field of computational fluid dynamics, CFD, comes in, and where the story takes a turn that connects turbulence to some of the biggest computers ever built. The challenge is this: If you want to directly simulate a turbulent flow, resolving every eddy all the way down to the Kolmogorov microscale, the number of grid points you need scales roughly as the Reynolds number to the 9/4 power. For the flow around a commercial aircraft at cruising conditions, the Reynolds number is on the order of tens of millions. Do the math, and you'd need something like 10 to the 16th grid points. That's 10 quadrillion. And at each grid point, at each time step, you're solving coupled nonlinear partial differential equations. Even with the fastest supercomputers available today, a direct numerical simulation of the flow around a full aircraft is simply not possible. Not today, and not for decades to come, if ever at that scale. So engineers had to get creative. They had to find ways to cheat. Not cheat exactly, but to find shortcuts that capture the important physics without resolving every tiny swirl of fluid down to the millimeter scale. And the story of how they did that is one of the most practically important chapters in all of fluid dynamics, because it's the story of how we actually design the things we use every day. The first and most widely used shortcut is something called Reynolds Averaged Navier-Stokes, or RANS, and the idea behind it is beautifully pragmatic. You take the Navier-Stokes equations, those same impossible, beautiful, nonlinear equations that Navier and Stokes wrote down in the 19th century, and instead of trying to resolve every fluctuation in the turbulent flow, you split the velocity at every point into two parts, a time-averaged mean and a fluctuating component. You're essentially saying, look, I don't care about the exact instantaneous velocity at this point. I care about the average velocity, the one that would emerge if I sat here with a sensor and averaged over a long period of time. The fluctuations are turbulence, and they matter, but maybe I can model their effect on the mean flow without tracking each one individually. When you substitute this decomposition into the Navier-Stokes equations and average everything out, something interesting happens. You get equations that look almost like the original ones, but with extra terms that represent the effect of the turbulent fluctuations on the mean flow. These extra terms are called Reynolds stresses, named after Osborne Reynolds, the same Reynolds from the pipe flow experiments. And here's the problem. These Reynolds stress terms introduce new unknowns. You've got more unknowns than equations. The system isn't closed. This is called the closure problem of turbulence, and it's one of the central headaches of the entire field. To close the system, you need a turbulence model, some additional set of equations or assumptions that tells you what those Reynolds stresses are, approximately, in terms of quantities you already know. And this is where things get fascinatingly messy, because there is no single correct turbulence model. There are dozens of them, hundreds if you count variations. Some are simple, just one extra equation. Some are complex, two equations, or even more. The most famous one is probably the K-epsilon model, developed in the late 1960s and early 1970s, largely through the work of Brian Launder and Dudley Spalding at Imperial College London. The K stands for turbulent kinetic energy, the energy contained in the fluctuations, and epsilon stands for the rate at which that energy dissipates. You write transport equations for both of these quantities, and then you use them to estimate the Reynolds stresses. It's approximate. It's imperfect. But for a huge range of practical engineering flows, flow through pipes, over flat plates, around bluff bodies, it works remarkably well. Well enough to design things, well enough to trust. And that's really the key insight here. Engineering doesn't need perfection. Engineering needs good enough. Good enough to predict the drag on a car body within a few %. Good enough to estimate the pressure drop through a heat exchanger. good enough to identify where flow separation will occur on a wing so you can reshape it before you build the wind tunnel model. RANS with a decent turbulence model gives you that, and it does it on a desktop computer in hours rather than requiring a supercomputer running for months. But here's the thing. RANS has blind spots. There are flows where it struggles, sometimes badly. Flows with massive separation, where the wake behind a bluff body is chaotic and unsteady. Flows with strong swirl, like inside a cyclone separator or a combustion chamber. Flows where the turbulence is highly anisotropic, meaning it's not the same in all directions, which violates assumptions baked into simpler models. And this is where engineers started reaching for something in between RANS and full direct numerical simulation, something that resolves the big turbulent structures, the ones that carry most of the energy and do most of the mixing, while modeling only the small ones. This approach is called large eddy simulation, or LES, and it's one of the most elegant compromises in all of computational physics. The idea traces back to the meteorologist Joseph Smagorinsky, who in 1963, working at the Geophysical Fluid Dynamics Laboratory in Princeton, proposed a way to simulate atmospheric circulation by explicitly computing the large-scale motions while parameterizing the effect of small-scale turbulence with a simple model. His sub-grid scale model, as it's called, assumes that the unresolved small eddies act like an enhanced viscosity, smoothing things out at scales below the grid resolution. It's a rough approximation, but Smagorinsky's insight was that the small eddies are more universal, more predictable, more isotropic than the large ones. They're the ones that Kolmogorov's theory describes well. So even a crude model for them can work, as long as you're resolving the big, energy-containing eddies properly. Think about it this way. Imagine you're watching a river from a bridge. You can see the large swirling patterns, the big eddies behind a rock, the slow rotation of water in a bend. Those large structures are unique to this particular river, this particular rock, this particular geometry. But if you could zoom in and look at the tiniest swirls, the ones just millimeters across, they'd look pretty much the same in any turbulent flow at similar conditions. They're generic. They're universal. LS exploits that universality. Resolve the unique stuff, model the generic stuff. The computational cost of LES falls somewhere between RANS and direct numerical simulation. It's much more expensive than RANS. You need a finer grid, and you need to run the simulation in time, capturing the unsteady evolution of those large eddies, which means thousands or millions of time steps. But it's vastly cheaper than DNS because you don't need to resolve down to the Kolmogorov scale. For many engineering problems, LS has become the gold standard when accuracy matters and you can afford the computational time. It's used extensively in combustion research, in aeroacoustics. That's the study of noise generated by turbulent flows, like jet engine noise, and increasingly in automotive and aerospace design. And then there's a hybrid approach that splits the difference even further. It's called detached eddy simulation, or DES, and it was developed in the late 1990s by Philippe Spallart and others. The idea is clever. Use RANS in the regions where it works well, like attached boundary layers close to walls, and switch to LES in the regions where RANS struggles, like separated wakes and free shear layers. You get the efficiency of RANS where the flow is well behaved and the accuracy of LES where it's not. It's a pragmatic, engineering-minded solution, and it reflects something deep about how this field has always worked. You use the right tool for the right part of the problem. You don't insist on one approach everywhere. Now, all of this computational work requires something that would have been unimaginable to Navier or Stokes, or even Reynolds. It requires computers, and the history of CFD is inseparable from the history of computing itself. Some of the earliest digital computers were used for fluid dynamics calculations. The ENIAC, one of the first general-purpose electronic computers, completed in 1945 at the University of Pennsylvania, was used for calculations related to hydrogen bomb design. And the physics of a nuclear explosion is, at its heart, a fluid dynamics problem. An extraordinarily violent one, with shock waves and radiation and extreme temperatures, but fluid dynamics nonetheless. John von Neumann, the brilliant mathematician who helped design the architecture of modern computers, was deeply interested in numerical methods for fluid dynamics. He recognized early on that the Navier-Stokes equations, unsolvable by hand for anything interesting, were perfectly suited to machine computation. You discretize the domain, break it into a grid of points, write approximate equations relating the values at neighboring points, and march forward in time, updating everything step by step. It's mechanical. It's repetitive. It's exactly what computers are good at. Von Neumann and his colleagues at the Institute for Advanced Study in Princeton developed some of the foundational numerical methods for solving partial differential equations on computers in the late 1940s and early 1950s. And one of the things they discovered, or rather rediscovered in a new context, was that numerical methods for fluid dynamics can go spectacularly wrong if you're not careful. There's a concept called numerical stability, and it's a subtle but critical issue. If your time step is too large relative to your grid spacing, or if you use the wrong kind of approximation for certain terms in the equations, the errors in your calculation don't stay small. They grow. They amplify exponentially, and within a few hundred time steps, your beautiful simulation has blown up into meaningless noise. The Courant Friedrichs-Lewy condition, published in 1928 by Richard Courant, Kurt Friedrichs, and Hans Lewy, years before digital computers even existed, established the fundamental limit. Information in the numerical simulation can't travel faster than information in the physical flow. If it does, the simulation becomes unstable. It's a beautifully simple idea with profound practical consequences, and every CFD code ever written has to respect it. So by the middle of the 20th century, you had this remarkable convergence. You had the equations, Navier-Stokes, written down over a century earlier. You had the physical understanding, Prandtl's boundary layers, Reynolds' turbulence insights, Kolmogorov's statistical theory. You had the computational methods, discretization schemes, stability criteria, turbulence models, and you had the machines, computers that doubled in power every few years, following a trajectory that would eventually put more computing power in your phone than existed in the entire world in 1960. What you needed next was to put it all together and use it to solve real problems, and one of the most dramatic arenas where this happened was aerospace. The story of CFD in aerospace really picks up speed in the 1960s and 1970s, and there's one name that keeps coming up in this era, a name that most people outside the field have never heard, but that anyone inside it knows well. His name was Anthony Jameson, and he was born in 1934 in England, trained as a mathematician at Cambridge, and eventually ended up working on some of the most consequential problems in aircraft design. What Jameson did, starting in the early 1970s, was develop practical numerical methods for computing the flow around entire aircraft configurations, wings, fuselages, the whole thing, using the transonic flow equations. Transonic flow is the regime where the aircraft is flying near the speed of sound, and it's particularly tricky because the flow is subsonic in some regions and supersonic in others, with shock waves forming on the wing surface. These shock waves cause a sudden jump in pressure and can dramatically increase drag. Designing a wing that performs well in transonic conditions is one of the hardest problems in aerodynamics, and before Jameson's work, it was done almost entirely through wind tunnel testing. Expensive, slow, and limited in the number of configurations you could explore. Jameson's codes changed that. By the late 1970s and into the 1980s, his methods were being used by Boeing, Airbus, and other manufacturers to optimize wing shapes computationally. You could test dozens of design variations on a computer before ever building a wind tunnel model. The savings in time and money were enormous. And the designs got better because you could explore regions of the design space that no engineer would have thought to try based on intuition alone. The supercritical wing, a wing shape specifically designed to delay and weaken the shock waves that form in transonic flight, was refined and optimized using these computational tools. Every modern commercial aircraft you've ever flown on has wings that were shaped, at least in part, by CFD. But here's what's really interesting about this story, and it connects back to everything we've been talking about. Even with all this computational power, even with Jameson's elegant algorithms and ever faster supercomputers, the turbulence problem never went away. Those RANS turbulence models that engineers relied on, K epsilon, K omega, Spallart Almaraz, and all their cousins, they worked well for many cases, but they could also fail in ways that were hard to predict. A turbulence model that gave excellent results for one type of flow might give poor results for another. And the consequences of getting it wrong could be serious. If your CFD simulation underestimates the drag on a new aircraft design by even 5%, that translates to millions of dollars in extra fuel costs over the lifetime of the fleet. If it fails to predict flow separation on a control surface, you might discover the problem only in flight testing when changes are enormously expensive. This tension between the power of computation and the limitations of turbulence modeling is still very much alive today. It drives an enormous amount of research. Machine learning is now being applied to turbulence modeling, with researchers training neural networks on high-fidelity simulation data to develop better closure models. Direct numerical simulations, while still impossible for full aircraft, are being run for simpler canonical flows at ever higher Reynolds numbers, generating reference datasets that turbulence models can be tested against. And computing power continues to grow, pushing the boundary of what LES can handle, making it feasible for problems that would have been unthinkable a decade ago. And yet, for all this progress, there's something humbling about turbulence that persists. It remains, in some deep sense, unsolved. The Clay Mathematics Institute still has that $1 million prize waiting for anyone who can prove basic mathematical properties of the Navier-Stokes equations. The turbulence closure problem is still open, and every engineer who runs a CFD simulation knows, somewhere in the back of their mind, that the turbulence model they've chosen is an approximation. A good one, hopefully, a well-validated one, but an approximation nonetheless. There's a famous quip, often attributed to various people, that goes something like, "Turbulence is the most important unsolved problem of classical physics." Whether or not anyone actually said exactly that, the sentiment rings true. But you know what? This uncertainty hasn't stopped engineers from building extraordinary things. And that's maybe the most important lesson in all of fluid dynamics, that engineering has always been the art of making good decisions with incomplete knowledge. You don't wait for the perfect theory. You use the best tools you have, you validate against experiments, you build in safety margins, and you learn from failures. And speaking of failures, there are some in fluid dynamics that changed everything. Disasters that forced the field to confront what it didn't know and develop entirely new ways of thinking. One of the most dramatic involves not air, but water, and it starts with a dam in the mountains of northern Italy, in a narrow valley called the Vajont Valley. And the dam that stood there was, by every measure of structural engineering, a masterpiece. Completed in 1959, the Vajont Dam was a double-arch concrete dam, one of the tallest in the world at the time, 262 meters high, which is about 860 feet. Just picture that. A wall of concrete taller than the Eiffel Tower, wedged into a narrow alpine gorge, holding back a reservoir that was meant to generate hydroelectric power for northeastern Italy. The dam itself was brilliantly designed, thin, elegant, its double arch shape transferring the enormous pressure of the water into the rock walls on either side of the gorge. Structurally, it was a triumph. And here's the thing that makes the Vajont disaster so haunting. The dam didn't fail. The dam held. It's still standing today, in fact, if you go visit that valley. What failed was the understanding of the fluid dynamics and geomechanics of everything around the dam. On the night of October 9th, 1963, an enormous landslide, roughly 270 million cubic meters of rock and earth, detached from the slope of Monte Toc on the southern side of the reservoir and slid into the water at tremendous speed. Think about what that means. An entire mountainside, a volume of material nearly twice the volume of the reservoir itself, suddenly displacing the water. The slide hit the reservoir and generated a wave. Not a ripple, not a surge. A wave estimated at 250 meters high as it crested over the top of the dam. 250 meters. The water swept over the dam, poured down the gorge below, and obliterated the town of Longarone and several surrounding villages. Nearly 2,000 people died in a matter of minutes, and the dam stood there through all of it, barely damaged. Which tells you something profound about how we think about engineering systems. You can design the most perfect structure in the world, but if you don't understand the fluid dynamics of the environment it sits in, the way water interacts with soil, with rock, with slopes, with gravity, you haven't actually solved the problem. The engineers who designed the Vajont Dam were brilliant at concrete and arches and stress analysis. But the geology of Monte Toc was unstable. There had been warnings. Smaller landslides had occurred during the filling of the reservoir. The water level had been raised and lowered experimentally, and each cycle seemed to lubricate the clay layers within the mountain, making the slope more prone to movement. Geologists had raised alarms. Some of them were ignored. Some were underestimated. And the critical question, what happens if the entire slope lets go at once, was never adequately answered before it was too late. The fluid dynamics of what happened that night are staggering to think about. When you drop that much solid material into a body of water that fast, you're not dealing with gentle displacement. You're dealing with something closer to an impact event. The water has nowhere to go except up and out. The wave dynamics involve the coupling between the solid slide material and the water, a multi-phase flow problem of extraordinary complexity. The speed of the landslide, estimated at nearly 100 kilometers per hour, meant the water was displaced almost instantaneously on a human timescale. The resulting wave wasn't just tall, it carried enormous momentum. And because the gorge downstream was narrow and steep, the water was funneled and accelerated as it descended toward Longarone. Now, in the decades since Vajont, this disaster has become one of the most studied events in dam engineering and in what we now call dam break and landslide-generated wave modeling, researchers have built physical scale models of the Vajont Reservoir, recreated the slide geometry, and used modern CFD techniques to simulate the wave. And what they've found is that the physics, while complex, was knowable, at least in principle. The tools to predict something like this existed in embryonic form even in the early 1960s, but the computational power to run those simulations didn't, and perhaps more importantly, the institutional willingness to take the geological warnings seriously enough wasn't there either. This is a pattern you see again and again in fluid dynamics disasters. It's rarely that the physics is completely unknown. It's that the physics is complex enough that people underestimate it, or that the models they're using don't capture the right phenomena, or that warnings from one discipline, geology in this case, don't get properly integrated with the engineering analysis. Fluid dynamics doesn't exist in a vacuum. It's always coupled to something, to structures, to geology, to weather, to human decisions. And speaking of coupling between fluid dynamics and structures, let's talk about something that happened 23 years before Vajont, because it's probably the most famous fluid dynamics failure in engineering history, and you might already know the name: the Tacoma Narrows Bridge. November 7th, 1940, in Washington State. The bridge that twisted itself apart in the wind. Now, this one is interesting because the popular explanation you often hear, that the bridge failed due to resonance, that the wind frequency matched the natural frequency of the bridge and caused it to vibrate more and more until it broke, is actually not quite right. Or at least, it's a significant oversimplification. The real story is more subtle, and it's deeply rooted in fluid dynamics. The Tacoma Narrows Bridge was a suspension bridge, quite slender and elegant for its time, designed by Leon Moissaieff, who was a highly respected bridge engineer. It had a span of about 850 meters, and its deck was unusually narrow and shallow compared to other suspension bridges. From the day it opened in July 1940, it had a tendency to oscillate vertically in the wind. Workers during construction had already noticed it bouncing, and after it opened, drivers would see cars ahead of them disappear and reappear as the deck undulated. People actually came to drive across it for the thrill. They called it Galloping Gertie. But on that November morning, something changed. The wind was blowing at about 67 kilometers per hour. Strong, but not extraordinary. The bridge began its usual vertical oscillations, but then it transitioned into a different mode of motion, a twisting, torsional oscillation. One side of the deck would rise while the other fell, then they'd swap. And this torsional motion grew and grew until the bridge tore itself apart. The whole thing was captured on film. It's one of the most dramatic pieces of engineering footage ever recorded. Remarkably, only one life was lost, a dog named Tubby, who was too frightened to leave a car on the bridge. The owner escaped, but the dog wouldn't follow. So what actually happened, from a fluid dynamics perspective? Here's where it gets fascinating. The key phenomenon is something called aeroelastic flutter, and it's fundamentally different from simple resonance. In resonance, you have an external force that happens to match a natural frequency, and energy builds up because each push arrives at just the right time. Flutter is different. In flutter, the structure and the airflow form a couple system where the motion of the structure changes the aerodynamic forces acting on it, and those changed forces amplify the motion, which further changes the forces in a self-reinforcing feedback loop. Think about it this way. As the bridge deck twists, the angle at which the wind hits, it changes. That change in angle changes the aerodynamic lift and moment acting on the deck. If the geometry is just wrong, if the deck is too blunt, too shallow, the wrong shape, those aerodynamic forces can end up pumping energy into the torsional motion instead of damping it out. The wind doesn't need to be gusty or oscillating at any particular frequency. A perfectly steady wind can cause flutter because the oscillation is generated by the interaction between the structure's motion and the flow, not by the flow alone. This is a deeply fluid dynamic phenomenon. It depends on how the air separates from the edges of the deck, how vortices form and shed, how the pressure distribution changes as the angle of attack shifts. And in 1940, this wasn't well understood at all for bridge decks. Flutter was known in the aerospace world. Aircraft designers had been dealing with wing flutter since the 1920s and 1930s, and there was a growing body of theory around it. But bridge engineers and aeronautical engineers didn't talk to each other much. Different worlds, different conferences, different journals. The idea that a bridge could behave like a wing in a flutter condition simply wasn't on the radar of the bridge engineering community. After Tacoma Narrows, that changed completely. The investigation into the collapse brought aerodynamicists and bridge engineers together for the first time in a serious way. Theodor von Karman. And yes, that's the same von Karman whose name is on the vortex street, the alternating pattern of vortices shed by a bluff body in a flow. Von Karman served on the investigation panel and helped establish that flutter, not simple resonance, was the culprit. And from that point forward, every major bridge design in the world incorporated wind tunnel testing and aeroelastic analysis. This is actually a beautiful example of how failure drives understanding in fluid dynamics. Before Tacoma Narrows, bridge aerodynamics barely existed as a discipline. After it, wind engineering became a fundamental part of structural design. The bridge decks you see today on long-span suspension bridges, those wide, streamlined, box-shaped cross-sections, they look the way they do because of what happened on that November morning in 1940. Engineers learned to shape the deck so that the aerodynamic forces damp out oscillations instead of amplifying them. They learned to add fairings, to use perforated barriers, to think about the cross-section the way an aircraft designer thinks about an airfoil. And this brings up something worth sitting with for a moment. Fluid dynamics failures tend to be spectacular because fluids store and transmit energy so effectively. A structural failure might be local. A beam cracks, a column buckles. But when a fluid system fails, the energy release can be catastrophic and widespread because the fluid carries that energy everywhere. A dam break sends water cascading for miles. A flutter instability channels wind energy into ever-growing oscillations. A pressure surge in a pipeline, what engineers call water hammer, can propagate at the speed of sound in the fluid, shattering pipes and fittings far from where the disturbance originated. Water hammer, actually, is one of those everyday fluid dynamics phenomena that most people have experienced without knowing its name. You know that loud banging or clanking sound your pipes sometimes make when you shut off a faucet quickly? That's water hammer. What's happening is this. The water in the pipe is moving. It has momentum, and when you suddenly close the valve, the water can't stop instantaneously. The kinetic energy of the moving water converts into a pressure wave, a spike of very high pressure that travels back up the pipe at the speed of sound in water, which is about 1,400 meters per second. That pressure wave bounces off fittings, reflects back, bounces again, and the pipe vibrates and bangs until the energy dissipates. In your house, it's annoying but usually harmless. In an industrial pipeline, say a hydroelectric penstock or an oil pipeline, water hammer can be devastating. Pressures can spike to many times the normal operating pressure, enough to rupture pipes, destroy valves, and cause serious accidents. The mathematics of water hammer were worked out in the late 19th century by Nikolai Zhukovsky, sometimes spelled Zhukovsky, a Russian scientist who also made foundational contributions to aerodynamics. In 1898, he published a formula relating the pressure rise to the fluid velocity, the fluid density, and the speed of sound in the fluid. It's elegant and simple, and it tells you something engineers need to know. If you're going to close a valve quickly in a high-velocity flow, the pressure spike can be enormous. And this connects to something broader about how fluid dynamics shapes the infrastructure around you in ways you probably never think about. Every time you flush a toilet, water hammer arresters in your plumbing system absorb the pressure spike so your pipes don't bang. Every time a jet lands and the thrust reversers deploy, the sudden redirection of high-speed airflow is managed through carefully designed nacelle geometries that prevent destructive flow patterns. Every time you drive over a long bridge in a crosswind and the car doesn't get buffeted off the road, that's because the bridge deck and the barriers were shaped using wind engineering principles that trace directly back to the lessons of Tacoma Narrows. But there's another class of fluid dynamics problem that might be the most consequential of all, and it operates on a scale so vast that it makes bridges and dams look like tabletop experiments. It's the fluid dynamics of the atmosphere and the ocean, the flows that determine weather, climate, and ultimately, the habitability of the planet. And the story of how engineers and scientists learned to model these flows is one of the great intellectual adventures of the 20th century. It starts, believe it or not, with a man sitting in an ambulance on the Western Front during World War I, doing arithmetic by hand between shifts carrying wounded soldiers, trying to predict tomorrow's weather by solving the equations of motion for the atmosphere using nothing but pencil, paper, and a slide rule. His name was Lewis Fry Richardson, and he was a Quaker pacifist who refused to fight but volunteered as an ambulance driver with the Friends ambulance unit in France. Between the mud and the shelling and the stretchers, Richardson worked on what he called a forecast factory, a scheme to divide the atmosphere into a grid of cells and compute how temperature, pressure, wind, and humidity would evolve at each cell using the fundamental equations of fluid dynamics. The same Navier-Stokes equations we talked about earlier, essentially, but applied to a thin shell of gas wrapped around a spinning planet. Think about the audacity of that for a moment. In 1917, while the Western Front ground on around him, Richardson sat down and tried to compute a 6-hour weather forecast for a single point in Central Europe. He divided the atmosphere into columns, assigned initial conditions based on real observational data from May 20th, 1910, a date chosen because good surface observations existed, and then he ground through the calculations by hand. It took him 6 weeks. 6 weeks of arithmetic to produce a single 6-hour forecast for a single location. And the forecast was spectacularly wrong. His predicted pressure change was about 100 times larger than what actually happened, a catastrophic failure on the face of it. But here's the thing. The method wasn't wrong. The idea was sound. What tripped Richardson up was partly bad initial data and partly a problem that would haunt numerical weather prediction for decades. He didn't properly balance the initial conditions. In the atmosphere, there are fast-moving sound waves and gravity waves that carry very little weather information but produce enormous pressure fluctuations if your starting data isn't perfectly balanced. Richardson's initial conditions contained tiny inconsistencies that the equations amplified into huge, spurious pressure swings. It's a bit like trying to measure the gentle rise and fall of the tide while someone's throwing boulders into the water next to you. The real signal gets drowned out by the noise. Richardson published his results in 1922 in a book called Weather Prediction by Numerical Process, and it's one of those works that was decades ahead of its time. He knew perfectly well that his method would only become practical when machines could do the arithmetic. He even imagined, and this is one of the most wonderful passages in the history of science, a vast hall filled with 64,000 human computers, each one calculating the weather for their little patch of the globe, coordinated by a conductor standing on a central pillar with a spotlight, speeding up the sections that were falling behind and slowing down the ones that were getting ahead. It's a vision of parallel computing, described in 1922, before electronic computers existed. Richardson was imagining in human form essentially what a modern supercomputer does when it runs a weather model. Now, fast forward to 1950. The war is over. Electronic computers exist. Remember ENIAC, the machine we mentioned when talking about CFD? And a team led by Jule Charney at the Institute for Advanced Study in Princeton, working on John von Neumann's computer, finally achieved what Richardson had attempted by hand. They produced the first successful numerical weather forecast using a simplified set of atmospheric equations. Charney was clever about it. He didn't try to solve the full equations the way Richardson had. Instead, he used what are called the quasi-geostrophic equations, which filter out those fast, noisy waves, the sound waves and gravity waves, and keep only the slower, meteorologically meaningful motions. By doing that, Charney sidestepped the exact problem that had torpedoed Richardson's forecast. The initial condition imbalances that had produced Richardson's wild pressure swings simply couldn't arise in Charney's filtered equations. Their first forecasts, computed on the ENIAC in 1950, took about 24 hours of machine time to produce a 24-hour forecast. So they weren't faster than the weather yet. The weather arrived before the forecast was ready. But the forecasts were reasonable. They captured the broad patterns of atmospheric flow over North America. And that was the proof of concept. From that point on, it was a matter of faster computers, better equations, finer grids, and more observational data. And the improvements came remarkably quickly. By the late 1950s, operational numerical weather prediction was running at weather services in the United States, Sweden, and the United Kingdom. By the 1960s, the models were three-dimensional, incorporating multiple layers of the atmosphere. By the 1970s, they included the effects of moisture, radiation, and the interaction between the atmosphere and the ocean surface. Each decade brought roughly one additional day of useful forecast skill. In the 1950s, you could maybe predict 2 days ahead with any accuracy. By the 1980s, it was 5 days. Today, a 5-day forecast is as accurate as a 2-day forecast was in the 1980s, and useful skill extends out to about 10 days for large-scale patterns. Here's what's really clever about how modern weather models work, and it connects directly to everything we've been talking about with CFD. The atmosphere is a fluid, a compressible, rotating, stratified, turbulent fluid, heated unevenly by the sun and bounded below by a complicated surface of oceans, continents, mountains, ice sheets, and forests. The equations governing it are essentially the Navier-Stokes equations, plus thermodynamics, plus moisture physics, plus radiation, all on a rotating sphere. You can't solve them analytically. Nobody can. So you discretize them onto a grid, just like Richardson imagined, and you march them forward in time, step by step. Modern global weather models use grid spacings of about 9 to 13 kilometers horizontally and have 60 to 100 vertical levels. That sounds coarse, and it is. A 13-kilometer grid can't resolve individual thunderstorms, which might be only a few kilometers across. So everything smaller than the grid has to be parameterized, which means represented by approximate formulas rather than explicitly computed. Convection, turbulence in the boundary layer, the formation of cloud droplets, the interaction of radiation with clouds. All of these processes happen at scales smaller than the grid and have to be handled through parameterization schemes. And this is where a huge amount of the uncertainty in weather and climate modeling lives. Not in the large-scale dynamics, which the equations handle well, but in the sub-grid scale physics that has to be approximated. It's the turbulence closure problem all over again, just in a different context. Remember how we talked about Reynolds averaged equations needing a turbulence model to close them? Same fundamental issue here. The atmosphere is turbulent at scales from millimeters to thousands of kilometers, and no computer on Earth can resolve all of those scales simultaneously. So modelers make choices about what to resolve and what to parameterize, and those choices have consequences. And this brings us to climate modeling, which is really weather modeling's longer, slower, more consequential sibling. A weather model asks, what will the atmosphere do over the next few days? A climate model asks, what will the statistical behavior of the atmosphere-ocean system look like over decades or centuries? The equations are fundamentally the same, but the challenges are different. For weather prediction, your biggest problem is initial conditions. You need to know the current state of the atmosphere very precisely, because small errors grow exponentially thanks to the chaotic nature of the flow. That's the butterfly effect, and it's why weather forecasts become useless beyond about 2 weeks, no matter how good your model is. Edward Lorenz discovered this in 1963, working with a drastically simplified set of atmospheric equations on a Royal McBee computer at MIT. He found that rounding his initial conditions from 6 decimal places to 3, a change of less than 1 part in 1,000, produced a completely different forecast after a few simulated days. Deterministic chaos. The atmosphere is a chaotic system, and there's a fundamental limit to how far ahead you can predict its detailed state. But climate is different. Climate is the statistics of weather, the averages, the variability, the extremes. And while you can't predict whether it will rain in London on March 15, 2050, you can, in principle, predict whether London will be warmer and wetter on average in 2050 than it is today. That's because climate is governed by energy balance. How much energy comes in from the sun, how much gets trapped by greenhouse gases, how much gets radiated back to space. And those are things you can calculate. The chaotic details of individual weather systems wash out when you average over long enough periods, and what remains is the response to the boundary conditions, the composition of the atmosphere, the configuration of the continents, the brightness of the sun. So climate models are, at their core, fluid dynamics models coupled to radiation physics and chemistry. They solve the same Navier-Stokes-derived equations on the same kinds of grids, but they run them for simulated centuries rather than simulated days, and they couple the atmospheric model to an ocean model, a sea ice model, a land surface model, and increasingly, a carbon cycle model and an ice sheet model. The ocean, by the way, is its own magnificent fluid dynamics problem. Ocean currents transport enormous amounts of heat around the planet. The Gulf Stream alone carries about a petawatt of thermal energy northward, which is roughly 100 times the total energy consumption of human civilization. The thermohaline circulation, driven by differences in temperature and salinity, overturns the entire deep ocean on timescales of roughly 1,000 years, and its behavior under changing climate conditions is one of the great open questions in Earth system science. And all of this, the weather forecasts on your phone, the climate projections that inform international policy, the hurricane track predictions that trigger evacuations, all of it rests on the same foundation we've been building throughout this whole conversation. It's the Navier-Stokes equations, discretized onto a grid, marched forward in time, with turbulence and subgrid processes parameterized because we can't resolve them directly. It's Euler's inviscid equations forming the backbone, with Prandtl's boundary layer ideas informing how we handle the surface. It's Richardson's dream of a forecast factory, realized not by 64,000 humans in a great hall, but by supercomputers performing quadrillions of floating point operations per second. And yet, for all that computational power, there are still things we struggle to get right. Clouds, for instance. Clouds are perhaps the single most important unsolved problem in climate science, and they're fundamentally a fluid dynamics problem. A cloud forms when moist air rises, cools, and the water vapor condenses onto tiny aerosol particles. But whether that cloud is a thin, wispy cirrus that lets sunlight through and traps outgoing heat, or a thick, bright stratocumulus that reflects sunlight back to space and cools the surface, that depends on the detailed microphysics of droplet formation, the turbulent mixing within the cloud, the large-scale circulation patterns that determine where the air rises and sinks. Clouds can either warm or cool the planet depending on their type, altitude, and thickness, and the net effect of clouds in a warming world, whether they'll amplify or dampen the warming, remains the largest single source of uncertainty in climate projections. It's a fluid dynamics problem wrapped inside a thermodynamics problem wrapped inside a chemistry problem, playing out at scales from micrometers to thousands of kilometers simultaneously. There's something almost poetic about that, if you think about it. We started this whole journey with Archimedes in a bathtub, noticing that water pushes back when you push into it. And now here we are, thousands of years later, using the intellectual descendants of that observation to try to predict the future of the planet's climate. The same fundamental physics, conservation of mass, conservation of momentum, conservation of energy, applied to fluids at every scale from a water pipe to the Pacific Ocean. And the thing that connects all of it, the thread running through every chapter of this story, is that fluids are simultaneously simple in their governing laws and staggeringly complex in their behavior. The equations fit on a t-shirt. The solutions fill supercomputers and still leave us with open questions. Which brings us to something I've been wanting to talk about. The places where fluid dynamics is pushing into genuinely new territory right now, where the questions aren't just refinements of old problems, but fundamentally new ways of thinking about what a fluid can do, what it can be, and what it can teach us about systems we never thought of as fluid at all. Take biological fluid dynamics, for starters. This is a field that's been around for a while in some form. People have studied blood flow and fish swimming for decades. But what's happening now is on a completely different level. Researchers are looking at the way organisms interact with fluids, not just to understand biology, but to steal ideas for engineering. And the reason this is so exciting is that evolution has had roughly 3.5 billion years to run experiments in fluid dynamics, and the solutions it's come up with are, frankly, humbling. Consider the way fish swim. For a long time, engineers assumed that the most efficient way to move through water was to minimize drag, make things smooth, streamlined, reduce turbulence. That's the submarine approach, the torpedo approach. But fish don't do that. Many fish actively create vortices, shed them in precise patterns, and then interact with those vortices to extract energy. A trout holding station behind a rock in a stream isn't fighting the turbulent wake. It's surfing it. It's using the vortices shed by the rock to generate thrust, slaloming between them in a way that actually requires less muscular effort than swimming in still water. Michael Triantafylou at MIT was one of the people who really pushed this understanding forward in the 1990s and 2000s, building robotic fish and showing that vortex interaction could dramatically improve propulsive efficiency. And the implications go beyond cute robots. If you can design underwater vehicles that harvest energy from turbulent flows instead of just fighting through them, you change the economics of ocean exploration, underwater sensing, long-duration autonomous missions. Or think about the lotus leaf. You've probably heard that lotus leaves are self-cleaning. Water beads up and rolls off them, carrying dirt away. That's a surface texture effect. Tiny microscopic bumps that trap air and create what's called a superhydrophobic surface. But the fluid dynamics of how droplets interact with those textured surfaces is extraordinarily rich. When a water droplet hits a superhydrophobic surface, it can bounce, it can pancake out and retract. It can even split into smaller droplets. The contact time, how long the droplet touches the surface, matters enormously for things like anti-icing on aircraft wings or self-cleaning solar panels. Researchers have found that by carefully designing the surface texture, you can reduce the contact time of a bouncing droplet below what was thought to be a theoretical minimum. The droplet doesn't retract symmetrically back into a sphere before bouncing. Instead, it recoils asymmetrically, breaking into lobes that leave the surface faster. That's a fluid dynamics insight with direct engineering applications, and it came from watching what nature does with surface geometry. Here's another frontier that's genuinely wild: active matter. This is what happens when you have a fluid, or something that behaves like a fluid, where the individual particles aren't passive. They're not just getting pushed around by pressure gradients and viscosity. They're self-propelled. Think of a dense school of fish, or a bacterial colony, or a swarm of tiny robots. Each individual is generating its own forces, making its own decisions, and the collective behavior that emerges looks like a fluid. It flows, it swirls, it forms patterns, but it doesn't obey the Navier-Stokes equations in any straightforward way. Active matter can do things that no ordinary fluid can. It can spontaneously start flowing without any external force. It can exhibit what physicists call giant number fluctuations, where the density variations are much larger than you'd expect from thermodynamics. It can form structures, vortices, jets, bands of collective motion, that arise not from boundary conditions or pressure differences, but from the internal activity of the particles themselves. This is a place where fluid dynamics meets statistical physics, meets biology, meets robotics. Researchers like Sriram Ramaswamy in India and Cristina Marchetti at UC Santa Barbara have been building the theoretical frameworks for active fluids, writing down the equations of motion for these systems, and discovering that many of the tools from classical fluid dynamics carry over, but need to be modified in fundamental ways. The symmetries are different. The energy input isn't at the boundaries. It's distributed throughout the fluid at the scale of every single particle. And the results are strange and beautiful. Dense bacterial suspensions can reduce the effective viscosity of the fluid they're swimming in some cases, driving it to zero or even making it negative, which means the fluid appears to push in the direction of motion rather than resist it. That's not a violation of physics. It's a consequence of the bacteria pumping energy into the flow at every point. But it's deeply counterintuitive, and it opens up possibilities for things like microscale mixing, targeted drug delivery, self-organizing materials. And then there's the intersection of fluid dynamics with machine learning, which we touched on earlier, but which is evolving so rapidly that what was cutting edge 2 years ago already feels like history. The early applications were mostly about speeding up simulations, training a neural network to approximate what a CFD solver would produce, but faster. That's useful, but it's not transformative. What's transformative is using machine learning to discover things about fluid dynamics that humans haven't figured out yet. Here's what I mean. Turbulence closures, those models we talked about, the ones that try to capture the effect of small-scale turbulence on the large-scale flow, have been built by humans using physical intuition, dimensional analysis, and calibration against experimental data. They work reasonably well for many flows, but they fail for others, and improving them has been painfully slow. Now, researchers are training neural networks on high-fidelity simulation data, direct numerical simulations of turbulence, the kind that resolve every eddy, and asking the network to learn the closure relationship directly from the data. The network doesn't know about Kolmogorov's theory or the log law of the wall or any of the traditional turbulence modeling assumptions. It just sees inputs and outputs and finds patterns, and in some cases, the closures it discovers outperform anything humans have come up with. Julia Ling and Jeremy Templeton at Sandia National Laboratories published some of the early work on this around 2016 using neural networks embedded with known physical symmetries, so the network can't violate things like Galilean invariance or rotational symmetry. And the results were striking. The models generalized to flows they weren't trained on, which is the real test. But here's the deeper question, and it's one that keeps fluid dynamicists up at night. In a good way. If a neural network discovers a better turbulence model, but you can't interpret what it's doing, have you really learned anything? Is it science, or is it just a very good lookup table? This is where the field of interpretable machine learning meets fluid dynamics, and it's genuinely fascinating. Some researchers are using techniques like symbolic regression, where instead of training a black box neural network, you use algorithms to search for simple mathematical expressions that fit the data. The idea is that if the underlying physics has a compact mathematical form, and we have good reason to believe it does, because physics tends to be elegant, then the algorithm should be able to find it. And sometimes it does. Stephen Brunton and Nathan Cutts at the University of Washington have been pioneers in this area, developing methods that can rediscover known physical laws from data, and more excitingly, find new ones. Their Cindy algorithm, sparse identification of nonlinear dynamics, takes time series data from a dynamical system and finds the simplest set of differential equations that reproduce the behavior. When you apply it to fluid systems, it can pull out governing equations that look like physics, that are interpretable, that you can analyze with traditional mathematical tools. That's not just engineering. That's discovery. Now, let me bring this back to something more tangible, because I don't want to leave you floating in abstraction. Think about the air around you right now, wherever you are, in a bedroom probably, given that you're listening to this. The air in that room is a fluid, and it's doing things. It's circulating, driven by tiny temperature differences. The warmth from your body is creating a thermal plume, a gentle column of rising air that peels away from your skin and drifts upward. If you're under a blanket, there's a whole microclimate of trapped air being warmed by your body and slowly exchanging with the cooler room air through the edges and folds of the fabric. The air you're breathing out is warmer and more humid than the air you're breathing in, and it rises and mixes with the room air in a turbulent jet, that dissipates within about a meter or so of your face. Every one of these processes is governed by the same equations we've been talking about all night, the same Navier-Stokes equations that describe hurricanes and ocean currents and the flow over an airplane wing. The physics doesn't change, only the scale changes, and with it, which terms in the equations matter most. And that's something worth sitting with for a moment. The universality of it. The fact that the same mathematical framework that Navier and Stokes wrote down in the 1800s, building on Euler's work from the 1700s, building on Newton's laws from the 1600s, building on Archimedes' observations from the 200s BC. That same framework describes the flow of blood through your capillaries, the weather system moving across your continent right now, the plasma jets erupting from the surface of the sun, the accretion disk spiraling into a black hole. Fluids are everywhere. They are, in a very real sense, the medium through which most of the universe's interesting behavior happens. Stars are fluids. The Earth's mantle is a fluid on geological timescales. It convects. It has plumes. It has boundary layers. The traffic on a highway behaves like a compressible fluid, with density waves and shock-like phenomena when cars brake suddenly. Even crowds of people flowing through corridors and stadiums can be modeled using fluid dynamics equations, and those models are used to design evacuation routes and prevent crushes. So when you hear fluid dynamics, I hope it no longer sounds like a narrow technical specialty. It's one of the broadest, most connected branches of physics and engineering there is, and the fact that it remains in many ways unsolved, that the fundamental equations are still beyond our ability to fully analyze, that turbulence still doesn't have a complete theory, that the Clay Mathematics Institute is still waiting for someone to prove whether smooth solutions to Navier-Stokes always exist. That's not a failure. That's an invitation. It means there are still deep things to discover, still fundamental surprises waiting, and I find that comforting, honestly. In a world that can sometimes feel like everything important has already been figured out, fluid dynamics is a reminder that nature still has secrets, that water flowing over a stone in a stream is doing something that the most powerful computers on Earth can't fully predict. That the coffee cooling on your nightstand, if you left one there, is undergoing convective patterns that connect, through an unbroken chain of physics, to the circulation of the Earth's atmosphere and the dynamo that generates our planet's magnetic field. We started tonight with Archimedes, lowering himself into a bath and noticing something fundamental about displacement. We traveled through centuries of people trying to write down the rules that fluids follow. Euler with his inviscid equations, Navier and Stokes adding viscosity, Reynolds watching dye filaments break into chaos, Prandtl resolving D'Alembert's paradox with a thin boundary layer, Richardson trying to forecast weather by hand in a war zone, Lorentz discovering that determinism doesn't mean predictability. We talked about real disasters and real triumphs, about equations that fit on a t-shirt, and solutions that fill warehouses of computing time. We talked about the cascade of energy from large eddies to small ones, about the 5/3 law, about the quiet genius of Kolmogorov working in Moscow while the world burned around him. And now, here at the end, the thing I want you to carry with you, or carry into sleep, more likely, is just this. Every fluid you encounter, every stream of water from a faucet, every gust of wind against your face, every curl of steam rising from a cup, is a small performance of some of the deepest physics we know. It looks simple. It is not simple. It is, in fact, one of the hardest problems in all of mathematics and physics, playing out casually, constantly, everywhere around you, all the time. And the people who've spent their lives trying to understand it, from Archimedes to the graduate student running simulations right now in some lab somewhere, waiting for results at 3 a.m, they've all been pulled in by the same thing. The way a fluid moves is beautiful, and the reasons it moves that way are deep, and the deeper you look, the more there is to find. So let that thought settle. Let the complexity of it all become not a source of anxiety, but a kind of lullaby, the reassurance that the world is richer and more intricate than we can fully grasp, and that's okay. The equations are still there, governing everything, whether we solve them or not. The water still flows. The air still moves. And somewhere right now, a fluid is doing something no one has ever fully explained, and it doesn't mind at all. It just flows.